Hi, welcome to Lesson 23b, Discrete Probability Distributions. The goal of today's lesson is to learn what discrete probability distributions are and how they are used. We've been talking about probability for a while, and we're now going to be looking at the distribution of those probabilities, and it's kind of like frequency distributions. When we looked at frequency histograms, etc., it's the same sort of idea, but we're talking about probabilities and the idea that different probabilities will have a different, obviously, certainty that the event will occur. So the distributions of these probabilities could be represented either in a table or in graphical form or in function form. And the function form, it can be called a probability distribution function, or it's also seen as a probability mass function. Either way, it's the same sort of idea that I'll show you in a second. So if we're going to construct a probability model, it's necessary to assign a numerical value to each outcome. So outcomes could be like, again, flipping a coin. We've got heads or tails. Or flipping two coins, for example. We'd have, head head, head tail, tail head, and tail tail. So if we were interested in, for example, the probability that one head occurred, then we would say that x equals 1. So we're finding the probability of x equals 1. So this can be used to determine the probability when one head has turned up. Of course, the other probabilities are when 0 heads turn up, that would be the two tails, and of course the last possible outcome would be when x equals 2, which is 2 heads turning up. So of course all of these have specific probabilities, and we have to take into account all of these probabilities when creating the probability function or the probability distribution. So there is a certain rule that all these probabilities have to follow. The random variable that we're going to be looking at, in this case the random variable is x. It's a discrete random variable that could equal 0, 1, or 2. And so x, our discrete random variable, has a sample space of x1, x2, x3, etc., all the way up to x sub n. So these are all the possible outcomes that you could see in the event. And then each of these events, or each of these outcomes, would have a certain probability, and that could be listed like this. And the probabilities have a set of p sub 1, p sub 2, etc. Not that this is all that useful at the moment, but for each of these outcomes there is a corresponding probability. So then, to tie these two things together, the probability of the discrete random variable when it equals outcome I, that's an I, that equals the probability. So the probability of this occurring is this value. And I, of course, so this is the general term, or the general way of expressing that each of these different outcomes have a probability that gives you a value. And I is all the different, the variety of subscripts that go from 1 to n. Okay, so covering 1 to n for all these outcomes and all the corresponding probabilities, which can be written in this form. So just simplified, the probability that the random variable will take on this value, which is the outcome, will be this value. And that probability value, this is a lowercase p, which you may not be able to tell, this is supposed to be an uppercase p. These values would take on decimal values or even percentages, but generally they'll be decimal values. So when we take all of these into consideration, all of the possible outcomes with all of their possible probabilities, when we look at all the probabilities, when we look at I equals 1 to n, then if we look at all these probabilities, all the probabilities are going to be between 0 and 1. From uncertain, or sorry, unlikely, or not, impossible, sorry, that is impossible, to definitely certain, and all the different probabilities in between. So when we look at the probabilities of all of these outcomes occurring, all these probabilities for this event, whatever that may be, will range between 0 and 1. Then if we were to add all these up, so remember when we looked up here, looked at this in another video before, when the outcome was one head occurring, that's basically 50% of the time it would occur, so it's a 50% probability that that would occur, because that's 2 of the 4 possible outcomes. When no heads turn up, that is 2 tails, that's a 1 in 4 probability, and when 2 heads turn up, there's a 1 in 4 probability. So if you add up all these different probabilities, they're going to equal 1, because with all certainty, when you flip 2 coins, one of these scenarios will definitely occur. Okay, so then we can do the same thing for any sort of event. So the sum, if we go from I equals 1 to n, so we're looking at all the different probabilities, that's going to equal p sub 1 plus the probability 2 plus p sub 3 all the way up to p sub n, and when you add all those together, they will always equal 1. Okay, just like in this example here, when you take the probabilities of all the different outcomes that could occur during an event, the fact that we will definitely get at least one of those. So the sum of all those probabilities, meaning that one of those will definitely have to happen when we do the experiment or look at the event. So that's why it's going to equal 1, because one of these definitely will have to happen. Okay, so just to quickly recap, one of the events, one of these outcomes is going to happen. Therefore, if we add up all the probabilities that correspond to each of those outcomes, because with certainty at least one of those will occur, that's why the sum of all the probabilities will equal 1. And the last condition of these probability distributions, which is nothing really too earth-shattering, is that the set of all these probabilities describes the probability distribution of x. Now when we look at the probability distribution function, or what's also called the probability mass function, we say that the probability mass function is equal to the random variable when it equals a specific value. The domain of this is a set of all possible values of the variable, so all possible values of the outcome. And the range is all the set of values in the probability distribution of that variable. So if we've got the values 0, 1, and 2, that's the that's the domain, and the distribution is the range of that probability function. Okay, so that's something we'll look at some examples in class tomorrow. Okay, so now when we look at discrete random variables, we are certainly going to be looking at the probabilities when the random variable equals a specific number, but we're also going to be looking at intervals that the variable can take. Okay, and it's going to be important that we look at the intervals of, or the endpoints of the intervals and what they actually mean. So when we say the probability of x equals 5, it just means that probability that x equals 5. Okay, easy enough. This means the probability that x is less than 5. Then this is where it starts to get a little tricky when we do less than or equal to 5. So it's less than or equal to, meaning that it cannot be greater than. So this is where we would say the probability that x is at most 5. Then we go to the other side, x is greater than 5. Okay, that's fairly self-explanatory. Then probability that x is greater than or equal to 5. So it's equal to or greater than 5, so it cannot be less than that. So this means that the probability that x is at least 5, but can also be greater than. So it's at least 5 and greater. Then of course we've got, say, 2 less than x less than 8, for example. And here we say the probability that x is between 2 and 8. Then probability that 2 is, or the probability that x is between 2 and 8 is written like that. And it can actually, this is between 2 and 8. Sorry about that. This means that it is at least 2, but no more than 8. Okay, so just like up here, this was the probability that x was at least 5 and could be greater than. This means that x is at least 2, but then no more than 8. Then when we have if we don't have the equal to symbol, we've just got the less than, x less than 2 is less than x less than or equal to 8. That's saying that x is more than 2, but no more than 8. Okay, so it could be equal to 8 and less than, but is definitely greater than 2, so it has to be 3 and above. And then of course we could have 2 less than or equal to x less than 8, and that means that x is at least 2, but definitely less than 8, which means it would be from 2 to 7. Okay, so those are there's a table of this in your graphic in your textbook that you can take a look at in section 23b, and that's all the kind of the nitty-gritty of it. It'll all come together when we see the examples in class tomorrow. What I would like you to do in the meantime, before we see those examples, is I'd like you to take a look at page 611 and take a look at example 2. Then take a look at example 3 on page 612. Then between pages 612 and 613, you can familiar yourselves with the practice exercises 1 to 5. Follow that by looking at example 4 on page 613. Of course, once again, with all these examples, allowing the self-tutor to talk you through the solution, and then take a quick look at practice exercises 8 to 11 on pages 613 to 614. Okay, so those are the that's the nitty-gritty of the lesson. This sort of terminology is important to kind of get a handle on, and these three things here, these three conditions, are things that you're going to have to pay attention to. That the probability is definitely between 0 and 1, and the sums of all those probabilities definitely equal to 1. And then of course this just makes up the set of the probability distribution of X. Okay, well, thanks for watching, and we'll see you in class.